Hi, my name is Bryan, and in this video I will give you a brief presentation of my paper named Cognitive Machinery and Behaviours. I'm currently doing a PhD at the Engineering School of Cognitics affiliated with EMS Laboratory of Bordeaux-INP in France. My research topic is about the interaction between humans and future systems using artificial intelligence. For 2 years now, I have been conducting a transdisciplinary bibliography on cognitive science and AI in order to try to understand how cognition works, whether it is biological or artificial. My hypothesis is that it's possible to describe a functional model of an information processing system that achieves human-level behaviors. This model will then serve to interpret and analyze human and artificial cognitive behaviors. I have named my proposed architecture IPSEL, which stands for Information Processing System with Emerging Logics. The IPSEL functional architecture is composed of 3 information processing systems that altogether achieve the perception and control of the environment along with vegetative, intuitive, and declarative behaviors. To be more specific, physical interactions of sensory organs with an environment produce information messages that reach the direct and intuitive systems. The direct system processes this information and outputs information commands that directly go to effector organs in order to control vegetative behaviors. The intuitive system also outputs information commands in order to control intuitive behaviors. This system disposes of learning mechanisms that allow it to modulate its output so as to adapt to the environment with respect to an objective function. From these learning processes, the intuitive system allows a declarative system to emerge. This declarative system takes induced concepts and logics to output conceptual sequences that act as new information source for the intuitive system processes. The architecture was first inspired by the experimental studies on human decision-making conducted by psychologist and Nobel Prize winner Daniel Kahneman. Then, it was considerably enriched by personal inputs that I have gathered from philosophers of the mind. I particularly want to credit Arthur Schopenhauer, Carl Jung, Immanuel Kant, Baruch Spinoza, and Denis Diderot for their pioneering and powerful works on human cognition. To give you a glimpse of the specificity of my proposition, I consider the mind as an emerging tool that the body uses for knowledge management, which is different from the paradigm in which the mind is the referential center that uses the body as a tool for accessing reality. To represent the proposed architecture, I use a formalism that I have created and named Cognition Flow Graph. In this formalism, cognition is seen as a huge graph where perceptions are represented as activities on a set of source units. Behaviors are activities on a set of sinks units. And cognition is a routing process that determines how activation signals flow through the graph to eventually reach sinks units for behavior production. We have named activation signals AP flows. To propagate AP flows, cognition consumes energy. As a reaction of this propagation, cognition also emits a second type of signal that we have called emotional response signals. It can be seen as a self-generated evaluation signal that acts as an objective function for learning mechanism of the system. AP flows have a persistency principle, meaning that the activation rises from a non-significant level to its maximum potential, and decreases from a significant level to a non-significant one. The objective of cognition is therefore to monitor the emotional response signals and keep them in desirable states while saving energy. To achieve this goal, the cognition graph disposes of three dynamic mechanisms that allow its structure to self-organize, and so modulating activation paths and consequent behaviors. In my formalism, knowledge is represented by the graph structure, which can also be seen as the long-term memory of the system. Meanwhile, the specifically activated part of the graph corresponds to the content of short-term memory. For knowledge management, three mechanisms operate. One of them allows the creation of paths between unconnected routing units or group of units. We can call this mechanism Hebbian learning. The second mechanism allows the modification of paths between routing units. It uses the emotional response signals as the evaluation function. We can call it reinforcement learning. The last mechanism is the degradation principle, which allows paths that remain unused for a while to be erased. From these three mechanisms, we can enunciate two dynamic principles. The first one ensures that routing units that are simultaneously activated will tend to grow connections. The second one guarantees that frequently activated paths will undergo more reinforcement, which can lead to the emergence of activation patterns. Now I will describe what part of the graph embodies the three functional systems of the heap-cell architecture. Direct system processing refers to the activities on the direct routes of the graph. By direct routes, I mean routes that have a single possible path to connect sources to sinks. Intuitive system processing refers to local activities on indirect paths of the graph. By indirect paths, I mean that they imply a notion of networks and allow path learning and cycles. The declarative system processing refers to activities on the indirect paths that are considered from a global point of view, in other words, a combination of local networks. So the intuitive and the declarative system are embodied by the same graph but considered as two different levels. It is this organization of this part of the graph which allows the declarative system to emerge. Because of space limitation from my article, I didn't detail this emergence mechanism on my paper, so I will take the opportunity of this video presentation to give more insight about this feature. I will go step by step for describing how concepts and logics are induced from environment interaction and then recalled for conceptual sequences production by the declarative system. I have represented the environment as this gray rectangle. A limited part of the environment is interacting with the sensory organ of the system. If there is a recurrent interaction, the associated paths will undergo more reinforcement and eventually differentiate themselves enough to form activation patterns, represented as the geometric form on the diagram. It can be seen as a classification process that recognizes patterns of physical interaction and represents them as a pattern of local path activation. Other sensory organs also benefit from this mechanism. From the global point of view, we see a unique combination of simultaneous local patterns of activation emerging. If this combination occurs multiple times, involved local networks will grow interlocal connection because of the Hebbian learning. It now forms a specific global network that we have called concept. During the agent's life, and if we still take a global point of view regarding its internal structure, concepts appear in a given order, as the agent experiences the environment. As I have stated earlier, activation flows are persistent, meaning that concepts that are activated remain as such for a given amount of time. Therefore, two concepts that appear close in the emerging sequence will grow inter-concept connections because of the Hebbian learning principle. I have depicted here on the right the space of concepts that the structure has learned to represent. We can see that concepts may be of various forms and shapes, and they can overlap each other. The dotted lines show the inter-concept connections that grow with respect to the emerging sequence of concepts. After enough experience, the space of concepts may look like to figure number 3. It is a space of concepts and paths that connect them, which have been differentiated because of the reinforcement learning principle. This is what we have called emerging logics, that distribute probability over ordinated concept association. On a different phase of activity, it is now possible for the structure to internally activate a concept from a partial activation. We call this concept reconstruction. Moreover, having grown inter-concept connection, it is now possible for the structure to infer a conceptual ordinated sequence by following induced logics. By doing so, internally activated concepts engender new local activations that do not come from environment interactions. It is by this means that the declarative system produces new sources of information for intuitive processes. We say that the declarative system produces a hallucinated environment conceptual representation. On this slide, I briefly resume key aspects of the heap-cell paradigm. I will not read them now, as it is basically things that I have already said or that you can find in the paper. I just want to add that not every aspect of the theory have been communicated yet. Further description of aspects such as free will, language, and other notions have been explored. Nonetheless, it is still a work in progress, and I would like to get to a mathematical definition and do a computer experimentation. To conclude my presentation, I would like to take a step back and discuss the Turing Test. The Turing Test is a man-man-machine game that serves as a comparative evaluation of machine intelligence. It may have been depicted as such because intelligence is a subjective attribute that requires a context and a reference to be established. Searle's argument was that grammatically correct sequences of symbols do not imply understanding. For me, that's why Turing puts two humans in the game. Two humans, when they communicate, may use forms of language that require a common world representation and sociocultural background for understanding implicit meanings. For example, let's say that the interrogator, labeled as C, is a 32-year-old male raised in London. If we replace the other man, labeled as A, with a 12-year-old female raised in a rural area of Japan, or with a 82-year-old born blind male raised in Peru, the intelligence evaluation of the machine labeled as B may be fairly different even if both human references speak a grammatically correct English. To succeed at the Turing test, an agent should be able to represent the world in the same manner humans do. Also, it should be able to learn socio-cultural construction. But these constructions are continuously evolving, arguing the need for the agent to be capable of learning continuously evolving logics. I thank you for your attention and for the opportunity.